In continuation of the previous video, where we saw what is an IO command and what are the different types of IO command and what is an IO interface. So in continuation with that, here we will see the block diagram of the IO bus. So the IO command, a typical IO instruction will contain three parts. I told you it will contain an opcode, a device address, and a function code. And then this is a overall block diagram. So you have a IO bus. So this is the CPU. So inside the CPU, the IO instruction is read, and from there the opcode is separated, device address is separated, and the function code is separated. So the device address is then separated and it is placed in the address lines and it goes to the IO bus. And then you see the function code is separated and it is placed in the function code lines, the control lines. Okay, and you have the accumulator register. So accumulator register is a special register which is used for arithmetic logic operations. This you would have seen in the previous chapter. So data from and to the accumulator will be placed in the data lines, and then you have the sense lines. You have the computer IO control. So the IO control, the input for the status command. I was discussing about a status command where the status of the peripheral. So if you look at here, you have the status register here. If the peripheral is ready to transfer data, okay, is ready to transfer data, certain bits in this register, status register, will be set. So the data from here, so will go to the sense lines. So this sense lines is directly connected to the computer IO control. So whenever the CPU issues the status command, so the peripheral controller will check whether the peripheral device is ready for transferring data either into the peripheral or outside the peripheral. So and then it will set the status bits accordingly, and then the CPU will issue a status command and check the status of the peripheral through the sense lines. Okay, so this is the block diagram, and in general, if you see the IO interface here, so this is the peripheral. So you have the peripheral and the peripheral controller. Okay, and you have the interface logic here. So you see that it is a two-way direction. The interface logic is connected in both ways. It's a bidirectional because of you have from interface logic data information has to pass on to the peripheral, and from the peripheral it has to come back to the interface logic for a read operation and for a write operation. So it is a bidirectional one, and you have a peripheral register and the status register. And then here you will see that this circuit here, you have an AND gate. And then so if the device address, I told you the each interface, each device will have a device address. So if the device address is let's say 1101, then this will be the decoder circuit. So you will have a 1 for 0, there is an inverter here, and then 1. So 1101. So this everything is given inside an AND gate. So the output. So when there is 1, when all ones are placed here in these lines, then the output of this circuit will be 1101 because there is an inverter here. So 1101. So like this you will have circuits for, this is one part of the circuit, decoder circuit. This is for this particular interface. So like this there will be so many interfaces which are connected to the different peripherals attached to the system. So for depending on the address of each peripheral, you will have some circuit. All these decoder circuits will be connected. Okay, and the device address will be placed in these lines, and the particular it will be placed in all the decoder circuits. So that particular, based on the design, the decoder will be designed in such a way that the output of each circuit will be the corresponding address of the particular interface. Okay, and then the function code. The function code will go to a command decoder. I told you there will be two decoders, one for decoding the address and the other one for decoding the command. So because the function codes for each peripheral, there will be different sets of function codes. So there to identify which function, which operation the peripheral controller has to activate, the control, there will be a decoder here, command decoder here. So this function code will be fed into this command decoder and everything. So you have the address, you have the buffer register. I told you the buffer register, once when everything is cleared, the data will be placed from the data lines. The data will be placed in a buffer register. Buffer register is a temporary register. So it will be placed in the buffer register, and from there it will go to the peripheral. Similarly, the reverse also. From peripheral, if there is a read operation, from peripheral it will go into the buffer register, and from the buffer register it will go to the it will go to the data lines, and from data lines it will go to the CPU. So this is the block diagram of an IO bus. Okay, now uh, so there are two types of, so we saw what is an IO bus. IO bus is in general, it contains some data lines. There's a group of wires. A bus is nothing but a group of wires. So in general, we have the IO bus contains some data lines, and then some address lines, and then control lines. So these three together is called an IO bus. So there will be transfer between a CPU and memory, and there may be transfer between CPU and IO device. Okay, so there are two different buses. One called an IO bus, which we saw earlier, and the other one called memory bus. So memory bus is for information transfers between CPU and the memory, and then again back from memory to CPU also. So IO bus is used for transfers between CPU and IO devices, and this we saw it is through the IO interface. There is no interface for transfer between CPU and memory, because memory is also an electronic device which is placed inside the system. So there will not be any the speed difference in speed mismatch in when there is a memory transfer. But there will be mismatch only when the transfer is between the CPU and the IO devices. So that is why you have an IO interface for IO bus. So these are the two buses, and these buses are required for transferring, for the data to be communicated from CPU to memory and back from memory to CPU, and from CPU to any IO device, and from IO device back to CPU. There are three ways in which these buses can be organized. Physically, there are three types of systems in which these buses can be organized. Okay, so the first one is you use separate buses. There might be, in some systems, there will be separate IO bus and there will be a separate memory bus. Okay, so you will have as a this is done when there is, in some systems you will have two processors, one the CPU and the other one is IO processor, which, as I told you, the CPU will not be disturbed for any of the IO operations. So there will be a separate processor which is called IO processor, which will take care of the of all the IO instructions. Then in that case, since this processor itself is separate, the buses will also be separate. So IO bus, there will be an IO bus where the IO bus will not be connected to your CPU, it will be connected to the IO processor. So whenever there is an IO instruction, it will be directed to the IO processor, and CPU will be free to take up some other job. So IO processor will then take it forward, will connect to the interface, through the interface it will connect the IO device through an IO bus. And between CPU and memory, transfer between CPU and memory will happen through the memory bus. So this in this case where there is a separate IO processor, there will be two buses, one separately for IO and another separately for memory. This is one way of organizing. This some systems will have like this. In some systems, there will be a common bus. There will not be a separate IO bus and a memory bus. There will be a common, common bus. So the bus will communicate to the IO devices as well as to the memory. So then in that case, there whether the CPU is accessing whether the IO instruction is for accessing the memory or whether the IO instruction is to access the IO device. That has to be differentiated because it's only a common bus. So in the previous method, there is a separate IO bus and there is a separate memory bus and there is a separate IO processor also. So there is no need for identifying it. It's very clear there. Whereas in this model, the bus is the same. So there is a common bus which is used to communicate both to the memory and to the IO. And but the instruction, whether it's an IO based instruction, whether the instruction is to connect to the IO or whether the instruction is to connect to the memory, that has to be differentiated. So how do we differentiate it? The distinction is made through separate read write lines. So you will have different control lines. Earlier you should not forget that the bus itself contains some data lines, some address lines and some control lines. Okay, it's together it's called a bus. So there will be this bus will be common for both IO as well as for the CPU. For memory for transferring data to the memory. So, but there will be separate control lines. So, when you have separate control lines, so the respective address will be placed in the address lines. Okay, and there will be a separate IO read write IO for connecting to the IO device and memory read write control lines. So the control lines, there will be more control lines. So whenever if the communication, the transfer is between CPU and memory, the address will be placed in the address lines and the respective read write, whether it's a read operation or a write operation, the respective control line for the memory control lines will be triggered, will be enabled, and the transfer, the communication between the CPU and the memory will be established. Okay, whereas if it is for the IO, then what will happen? The control lines, read and write control lines with respect to the IO will be placed in those will be activated. Those control lines will be activated, and the address will be placed there to activate the respective interface. Okay, and the data will be communicated between the CPU and the IO device. So this type of organization is called as isolated IO. The reason for the name isolated IO is the memory and the IO, since the bus may be common, but the control lines make it will make the bus either a memory bus or a IO bus. Bus is the same, the number of lines are the same. The same bus, at some point of time it will be act as a memory bus and some point of time it will act as an IO bus. That is what I am trying to tell you. Okay, so the IO interface addresses. I told you memory will have its own addresses, and the IO, you will learn about this addresses when you learn about the memory later on. So the IO interfaces will have some device addresses, and the memory will also have some addresses. Okay, so these IO addresses will now be different addresses will be allotted to the IO addresses and to the memory addresses. So that is why it is called it's called an isolated IO. So the different if the address will not be the same. Okay, so we are going to see a different organization in the next method. So there, which is called as memory mapped IO. Then you will understand the difference between the isolated IO and the memory mapped IO. So the second organization is you will have a common bus and the but separate control lines. So one to identify whether it's a memory transfer to memory, and the second set of control lines for IO separately. And the IO addresses, the IO interface addresses are entirely different. Different set of addresses are assigned to the IO interface addresses than from the memory. The memory will have a range of address. இதிலிருந்து இது வரைக்கும். This is the starting address of the memory and the ending address of the memory. It will be different. There will be a set of addresses assigned to memory. So there will be a set of addresses assigned to each device, IO device also. So device address. So this IO device will be there. It will not be the same. There will not be. It will be unique addresses. The address will not be. There will not be a match between the IO address and the memory address. So this type of organization is called as isolated IO. What is the next type of organization? Here we have a common bus and the control line is also common. Unlike the previous organization, to distinguish between a memory transfer and an IO transfer, where there is a separate control line, in the third type of organization, the control lines are also the same. So you have a common single bus system for both memory and IO, and with common control lines. Okay, so here, which means the IO address, how do the reason for having different control lines is to distinguish between the IO transfer and a memory transfer. Whereas in the third method, there is no distinction between the memory transfer and IO transfer. IO is now considered as a part of the memory itself. That is why there is no different separate control lines to distinguish, which means there will be a range of addresses for the memory, and within that range of addresses, a portion of the addresses will be allotted to for the IO interfaces. Okay, IO interfaces. That is why the same bus is used for both IO as well as memory. So what is the that and that is why the there is no different set of control lines to distinguish between a memory IO and a normal memory transfer and a IO transfer. Okay, so this type of organization is called as memory mapped IO. Memory mapped because a part of the memory itself is now considered for IO transfer. So when doing this, what happens is the memory has got a set of addresses and a part of that is now considered for IO. So which means the memory is now reduced. The size of the memory is now reduced. That is the range of memory will be reduced. So that is the main drawback of this memory mapped IO. So these are the three organizations and let us see the more about memory mapped IO. So in memory mapped IO, as I told you, there will be a single set of read-write control lines. Okay, and the memory and IO addresses share a common address space. So the the address space means starting address and the ending address. The whole thing, the range of address is called the address space. So within this address space, this is allotted for memory. Within this address space, some addresses will be allotted for the IO. So that is why the memory and IO addresses share a common address space. Okay, so a segment of total address space is reserved for interface. No specific input-output instruction. So since the address space is being shared by both memory as well as IO, the separate input-output instruction specifying memory instruction separately, IO instruction separately will not be there. So mostly in most of the processors, if you would have learned what an instruction is. There will be certain memory instructions there, and move instructions and all that. They are all memory instructions which directly access the memory. And there will be some IO instructions also. So here interchangeably it can be used. So IO instruction, there will be the specific. So because there are separate memory instructions and IO instructions in other system, in other isolated IO and other organization, other type of IO. So what happens is there will be a separate IO instruction and there will be separate memory instructions. There will be more memory instructions and less IO instructions. Whereas in memory mapped IO, since the address space is being shared by both memory as well as IO interfaces, there is no distinction between the memory transfer and the IO transfer. Meaning the more there will be there will be more number of IO instructions now. So all memory reference instructions can now be used for IO referring instructions also. So you will see that the it allows computer to use the same instructions for IO and memory transfer. So there are more memory reference instructions than IO typically in most of the systems. So now in memory mapped IO, all memory reference instructions will be available for IO transfer also. So the range of instructions will now be more. That is the main advantage of memory mapped IO.